Hello, this is the first of a series of review videos for the final exam. So here I want to talk about first order systems. Remember those? Yeah, that's way back, start of the semester. So first order systems, right? Well, maybe it would be helpful to remember the three characteristics that we use to describe systems in the first place. There was order, there was linearity, and there was homogeneity. Right? So if I had a system that looked like, oh, I don't know, something like that, where I just throw some constants at it. Oh, we can even get more irritating. There. This is a first order system because the highest derivative is a first derivative. That's first order. Is it linear? Well, every term that has an x in it it appears alone. X appears alone, and it's not squared or inside of a function or anything like that. So yeah, we are linear. It's cheating a little bit, but every system we're going to actually solve in this class, right, is going to be linear. And then homogeneity. Well, the trick there was, does x appear in every term? That is, are there terms that don't have x in it that appear like forcing functions, right? So, and we've had a lot of context now in the class to understand what that means, right? These are terms that are inputs that are driving the system, right? At the start of the semester, that was less clear, but now that should be really clear where that comes from. So another way to write this, same problem, in the context that might look a little more like the rest of the class. Let's see, it's just equal to, well, let's do it like this. Ha. All right, so those are so this is the kind of formula we might have gotten after modeling some first order system, and then we would solve it for a particular case by plugging in some function for y. All right, so let's get rid of this. That was a fun example, but let's actually work with this, because this looks like something I might give you on an exam, right? That looks like a great problem to give on an exam. Notice that b is the same in both coefficients. So solve. Oh, I don't know. We'll just call it x naught. Fine. And oh, excuse me. Oh, let's see. We need a new constant, don't we? Well, let's make y. Yeah, let's just do this. Ct squared. So here, y is going to be some. So it's a parabola, right? So y as a function of time looks like this. And of course, by tuning the coefficient c, you can adjust how quickly the input rises. And so the question is, what does x do? What does the output of the system do in response to that kind of an input? Okay. When we solve this, right, since we recognize that it's non-homogeneous, we've got to do this in two parts, right? We've got to solve it with a homogeneous solution and a particular solution. So step one, x of t is a particular plus a homogeneous solution. And we split this into two parts. I usually do the particular solution first. So the clever bit here is, how do we choose our particular solution? It's going to have to be in the same form as the forcing function. So it's going to have to be a parabola. So we need something that is a parabola in time, a second order polynomial in time. I'm running out of, I got to make some new coefficients. Let's see. Why don't we call these coefficients... I don't like using D. D is annoying. Well, we could use D, E, and F. I don't want to use E because that's the exponential, right? So, well, we'll just. I've already used C. I don't know why I'm so indecisive about this. We'll use S's. Why not? So S. There we go. Why not? For those of you doing Laplace, that's going to be pretty annoying, but oh well, deal with it. Alright, so we just have 3 coefficients. I'm calling them S because I'm running out of coefficients. I just grabbed S out of the sky. Alright, so let's plug everything into the original formula and see what works. So I need to know what the derivative of the particular solution is. It's going to be this. Right? In you plug, and we have this. Now I need the derivative to plug in here. And now we plug in the original particular solution. All right, and that's going to have to be equal to b times y, which is ct squared. There we go. Okay. So maybe this is worth just a moment's discussion. When we do this, remember what we do when we split the solution into the particular and homogeneous parts, right? Remember, the particular solution, its sole reason for existing is to cancel out the input, to be the system's response to the input. The homogeneous part deals with whatever's left, the initial conditions. That's its job. So we divide the solution into these 2 parts. Each part has its own job to do. That way we don't have to do it all at once, right? That's what gets hard when you try to do this for nonlinear systems. Okay, so let me get this in shot so we can see it. My lighting is in the way. All right. Some paper management problems. Okay, there we go. So there's where we are so far in trying to find our particular solution. Now we have our goal is to solve for these S1, S2, and S naught here in terms of A, B, C. Yeah, the coefficients of the original system, right? A, B, C. These A, B, and C are just numbers, right? So those are constants. They might be given. All right, so the way we do this, right, this looks like 1 equation, 3 unknowns. That's a problem. Remember, we set like terms of the polynomial equal. So let me just rearrange this to emphasize that. So there's my only squared term on t. All right, then here is going to be my linear term on t. 2a s2. All right, that's taken from this term and this term right here. I've combined them to form this term. And then I'm going to have 2 constant terms, one here and one here. So that one's going to be AS1 plus BS0, and that's the constant term, and all that is equal to BCT squared. All right, so remember A and B are system coefficients. So they're from my, A and B are coefficients from my system. C is from the forcing function. So it shouldn't shock us to see that C only appears in the forcing function, but A and B are littered throughout the problem, right? So that shouldn't be too terribly shocking. All right, now we just set like coefficients equal, so the squared terms are equal. The non-existent t term over here is going to be equal to that, so that's 0. Yeah, so here we go. BS2 is equal to BC. Well, that's not a coincidence. The b's cancel. Nifty. That implies that S2 is equal to C. We have one of our coefficients. Okay, next 2a s2 plus b s1 is equal to, well, 0. There is no t term, so this must be 0. Well, there we go. That implies, lovely, that implies that s1 is equal to, we're now looking for s1. We've already got s2. So s1 is going to be 2a s2 divided by b. How great is that? So we can substitute the c in to get rid of the unknown there. 2ac, excuse me, is negative. Whoops. Yeah, it's negative. So it's negative 2ac over b. All right, there's my s1. And we're going to do something similar for s0. Not so bad. So a s1 plus b s0 is equal to 0. Great. That implies that s0 is equal to negative as1 divided by b, which is equal to, well, just plug in s1. So we're going to have positive 2a squared c divided by b squared. Let me write what I've just learned. My particular solution is equal to ct squared, just plugging in s2 here, plus a negative 2ac over b times t, plus a positive 2a squared c over b squared, and that's it. That's my particular solution. Done. Now I need to go back and form my homogeneous solution. So just to review, we split the solution into two parts, particular and homogeneous. We now know the particular solution. The particular solution's job was to respond to this input. We've done that. We figured out what that is. We have found these coefficients, s2, s1, and s0, that fit into this equation when y is equal to this. Great. Okay. Next, we need to figure out how to obey this initial condition, because this doesn't do it. This only responds to the forcing function. It does not obey the initial condition. So for that, we need the homogeneous part. The homogeneous solution is always this. No creativity needed. There we go. So next. Yeah, no creativity needed here. We just plug that straight into our governing equation there. Remember this? There we go. Just to make sure it's clear what I did there. What did I do there? Remember the original equation was this, but the homogeneous form of the equation is this, where we get rid of the forcing function. So I've just plugged this into the homogeneous form of the governing equation. There we go. All right, that's easy. The e's cancel, they always do. The a's cancel, they always do. If you've done it right, they do. Lambda is negative b over a. So our final solution is there we go. Plus the particular solution. I'm not going to bother writing that again yet. So now we just need the initial condition. Now we just need the initial condition that x of time 0 is equal to x0, which is equal to, well, if I plug in 0 for time, I get a plus xp at time 0, which is equal to, at time 0, just this. This goes to 0, this goes to 0. So now I will write my total solution. So I have A. My value for A is x0 minus There it is. So if I were to plot this, I mean, we can mess with the shape of this plot massively by screwing around with these coefficients, right? But presumably the input forcing looked like this, right? So that was y, and the response might have, or the initial condition, right, might have been that here. So what we would see is it's going to fall in with this, but it's also going to lag it by a little bit. The system won't quite be able to keep up with the input. That's what we see here. So the response should look something like this if you actually plotted this mess. So the system would have an initial transience. Right, this is what we've talked about all semester, is these systems have some initial transients where they kind of settle into their solution, and then we settle into a quasi-steady state, right? And that's when you have just the particular solution left, and this has decayed away. Okay, well that was fun. Thanks for watching.